All right, and hopefully this is set up that Nick will be able to join us in a moment. We'll see. Okay. So the quiz, I'm still trying to make that happen. I ran into some technical difficulties. Okay, great. You are there. I will start presenting. Entire screen. Okay. All righty. So, yeah, the quiz, as you saw, is having some technical difficulties here. That was not the kind I was having with the quiz. For another class, a week ago, I had some issues with this class trying to get something to work. I learned something new every day. And it's one of these things that I guess I could punt and give you crappy stuff to do. I try to do better than that. It still might be crappy, but I'm trying to do better than crappy. And so, for instance, the quiz I was working on, it was giving me so much trouble. Took like 2,400 lines of code. So they're not a small task, to just throw some questions on a quiz. And so that can cause problems. However, we're slowing down a bit because now we're just modules are 2 weeks, and so hopefully that will help both you and me. And I opened up, so let's go to that. I opened up Module 3. It looks kind of sparse compared to the first two modules. I don't have due dates on the homework right at this moment. I should be able to, in the next 24 hours, have due dates on those over the next couple of weeks. But, certainly you can get started. There's not really anything much to speak of in the instructional content at this point. Couple videos, y derivatives 1 and y derivatives 2, and that's all that's there right at the moment. So I'll be working on that. Let's see. So, there's the homework. There's a discussion. Now, the discussion this module, you got lots of people. That all of these functions are named after people. Okay, so that's why I said people. But so lots of different items to choose from. Go look something up and try to figure out what it has to do with calculus. Some might be, that's kind of interesting. So if you happen to choose the Riemann function, you do have to do more than look it up. So I'll try to fix that. But so no, you don't get off easy just looking up the Riemann function. So you still need to explain how it relates to calculus and all that. So copy and paste, I guess, problem there. But again, lots and lots of different things to choose from. So you can get started on that. Now, the discussion in these modules, the discussion will be due on, and I just went with Monday, so a week from today at night. So that's the original discussion post will be due then. and then things like quizzes and projects and so forth will be due the next that following Sunday. So Sunday, September the 20th is the big time that way. Let's see. So, yeah, so the quiz project, there's nothing there right now. I know what we're doing for the project and so forth, but it's not all put together. I have no idea why there's is that always there? I don't know if that stuff there with the, I guess I'm number 277 or something. I don't know. But I've never noticed it not scrolling, so I don't know. But at any rate, yeah. So I know what we're doing with that. We're doing error again, but we're looking at it in a slightly different way. Something that relates to chapter 2, and I think that's what I have right now. Any questions about anything? Oh, and I need to, Nick might be talking, but I have him on, I had my speakers off, so I guess I didn't want to hear from him. But now, if that includes you, Nick, if you have any questions. Any questions on anything right now? Nope. Nothing. Okay. All right. Well, let's start by just kind of looking at this idea of tangent line and, hey, Jonah, you're first on the list here. What's a tangent line?
The only way I can describe it is like using trigonometry. Really, it's just like I can't even do that honestly.
Can't even do that. Okay, that's fine. Timbo, what's a tangent line?
Well, isn't it like there's a circle and then the line?
Okay, so you have a circle and a line.
Yeah, and they touch at the point at the edge of the circle.
Okay, so it's a line that touches at the edge of the circle. Aiden, did you have no, you were just like scratching your head or something like that. Oh, but you're next anyway, so.
Yeah, I pretty much just know what he said. It shows it like.
Okay, so we've got a circle and maybe a line that touches it. And we'll go, James, what do you think?
Yeah, I mean, that's everything up it's on.
Okay, so it's just a circle and a line. That's pretty much all we got. Anybody have anything different? Ah, that's what I was looking for. Touches on one point. And so typically when you are told about a tangent line at some point, often it's described as, in our case we're looking at functions, as sort of touching that function just in one place. Okay? And so, suppose I have a function, and we'll just take something real simple like f of x equals x squared. Okay, so I have that function, and now if I want to produce a tangent line to this thing, now Desmos is really nice this way. So what do I need to produce a line, a straight line? What information do I need to produce a straight line? And let's see, Anissa, what information do I need to make a straight line?
You either need a gradient, like a slope, and a point.
Okay, so I need a slope and a point.
Or you need 2 points.
Or I need 2 points. So we'll go with a slope and a point. And let's go with, I'm going to go in here to the point 1, 1. There's a perfectly good point. And now to get the slope, we're going to do something really nice. I'm going to say my slope is equal to f prime at 1. And Desmos just does it. Isn't that awesome? Now, it's doing it numerically, but, I mean, we're getting a very nice answer of 2. So there's my slope. And so if I do a line here, and I could call it y equals mx plus b, you know, something like that. I think I will do it this way. I'm going to say L of x is equal to, okay, I'm going to use my y value first. So I'm going to do, instead of m times x minus x1 and then plus y1, I'm going to switch the order and do y1 plus m times x minus x1. So y1 was a 1, because that's f of 1, and plus, and then my m times x minus x1, which was 1. Now, I can make this slightly more clear here in that I could say here, this is f of 1. Okay? And I get this nice straight line, and it appears to be touching that thing at a single point. Okay? So, wow, what a great idea for a tangent line. Now, unfortunately, that all falls apart in the sense of touching at just one point. If I all of a sudden change this to sine of x, okay? Oh, yeah, it still looks like it touches it in just one point, except not true. Touches it in 2 points. Okay, so locally, you can go, if you start using words like locally, I can kind of come in here, and if I get close enough in, yes, it appears to just hit it at one point. And I can kind of decide that, at least Desmos is deciding that for me, because if I click on either the straight line or the sine function, it shows me the intersection with everything else, and it's only showing me 1 point. So it appears it's only hitting in 1 point. And yeah, again, locally, sure, I can say that. But here's the way we want you to think of a tangent line. I say we. It's really me, but since I grade the papers and so forth, right, it's we. If I zoom way in, at some point, if I zoom in far enough, I can't see the difference between the two functions. So again, there's my point of intersection. But I've zoomed in far enough, well, maybe not quite far enough. It looks to me the top right, I might see a little bit of the sine function underneath there yet. So, I could zoom in a bit more, and now I'm pretty sure I can't see it. Okay? It looks like just one function being plotted, a nice straight line. So that's what we want you to think about when you think about a tangent line. And watch this. I'm so proud of myself. I'm remembering to go back to this. Okay, so the tangent line to a function at a point is the best straight line approximation. We'll go, I'll call it that. Straight line approximation to the function that passes through the point. That's what a tangent line is to us in calculus. It is the best straight line approximation to the function that passes through the point. Okay, so at any given point, I hopefully can make this tangent line. And so then that's why we care a lot about the derivative in many respects, is that I know how to work with straight lines really well. Okay, so I can work with straight lines well. Okay, I'm pretty good with straight lines. I can find things like intersections really easily. You know, I can talk about y-intercepts and x-intercepts. I can get the slope of a straight line very easily, that kind of thing. And so, because, really it comes down to, because I can do so much with straight lines, that's what makes this calculus thing work, is I know how to do stuff with straight lines. And that the key with a straight line is that its rate of change isn't changing. It's constant. Okay, so, we'll say a line's rate of change is constant. So that's what helps me out a lot. If you give me stuff that's easy, I can handle it. If it's hard, I can't. But if it's easy, I can. And so when you think of things like rate of change, well, if you tell me, hey, you're making $17 an hour, and then you say, oh, it worked for 8 hours, well, I can just take 8 times 17 and get the total number of dollars, something like that. That's really easy. I can do that sort of thing. And so we like this idea of straight lines. As far as their rate of change, it's easy. And that's part of the reason back in chapter P, it actually had you do a bunch of stuff with straight lines. Because that's really what we're doing in calculus. Okay, we're turning everything into little tiny straight lines. Because that picture I put up, right, I had to zoom way in to make it look like a straight line. But when I zoomed in far enough, yeah, it looked like a straight line. And so if I do that in enough places, I can talk about a more complicated looking thing like a sine function or a squaring function or something like that in terms of a bunch of straight lines as I go. That's also, to some extent, why they mention these piecewise functions back in chapter P. Okay? Because really that is what we're doing in calculus. We're taking everything and breaking it up into little pieces. And so since we've got, a line's rate of change is constant, and we use that sort of thing, again, like, you tell me the rate of change of something over time, say, and then I can add up all that and give you some kind of answer. We like that sort of thing. And so then a derivative at a point is the slope of the tangent line. At that point. Okay, so we've got a function. And if I tell you the derivative, what I'm telling you at a particular point, what I'm telling you is the slope of that tangent line. And so if I were to try to approximate that function at that point and locally at that point with a straight line, I would want its derivative to get that slope. But then I could use that straight line instead of that more complicated function. And actually in physics, we do that quite a bit with springs. Well, pendulums, that kind of thing. Springs and pendulums are really the same sort of thing. What we do is, to make our life much easier in physics, at least for small situations, we'll, if you're looking at the sine function that, does something like this, well, for small angles, what's a small angle? Well, like 10 degrees or less. So in radians, that's like, well, 15 degrees even. And radians, 15 degrees is like 0.25 radians. Figure, it's 57 point something radians, degrees per radian. It's around 57. So if you figure around 60 degrees for a radian, so if I go 15 degrees, that's about a fourth of 60, so about a fourth of a radian. But if you go into those small angles, actually the function y equals x, so this is sine of x, and then, here's the function y equals x. Those are really, really similar in there. Not much difference between them. And so that's a great approximation. It makes our life so much easier. If you have to solve something, sine x equals whatever, well, that's hard. I've got a calculator, so it's not that hard. But technically speaking, it's a hard thing to do. Whereas if I had x equals 2, I can solve that equation. All right, that's easy. I can do something like that. That's my kind of equation, right? It asks the question and gives the answer all at once. So, this is the kind of thing we're doing with these derivatives and why it's so helpful. And so, with that, what we want to do is look at our definition. So math definitions are very important. And the way we get our definition is that, so if I'm, looking at some function, and I would like to find the slope of that line, right, we can use this limit process to do it. We can do something like, okay, here is some x equals c, and there is f at c, and I would like to get the slope of that tangent line there. Well, it seems reasonable that if I pick some points out here, so here's a point, c plus, in your textbook uses that delta x thing. I really wish they'd just use an h, but it's just some small amount. We've just moved over some small amount. Then, again, with straight lines, what's really easy for me is to find that slope. Okay, so there is f at c plus delta x. And it's really easy for me to find that slope. And then what I could do is I could keep making delta x smaller and find that slope. And it seems reasonable that as I make that smaller, the limit of this thing ought to be the slope of that tangent line. Okay, because as I move in closer and closer, it seems like that should work. Well, so let me move out here a bit, because I'd zoomed in quite far. And actually, well, I don't know, that's fine. This will work. So I'll come in here and I'm going to use H. And so suppose I let, H equal 1. And now I probably don't, well, I could let it get negative as well. So I'm going to say this has to be between -1 and 1. And I'm just making a slider so I can kind of see what happens. And I am going to produce the line, through that point of the 2 points, f of c and f of c plus h. And still the point slope form idea, right? So I'll probably create the slope first. Now I'm going to go back here, and I'm just going to change that m to a f prime at 1, like that. And so that way I can reuse that m. I want to use it here. So my m here, I want to take f of x plus h. Whoops, not just the general x. 1 plus h minus f at 1. Okay, so I have that. And, yeah, okay. And then divided by h, because I'll have 1 plus h minus 1. So I just get h, or delta x on the bottom. Make that just a little bit wider. Okay, so right now h is 1, and I could also place that point out there just so we can see it. Here's the point 1 plus h, and f of 1 plus h. So there's my point. And now I'm going to make my line. I'll just call it y equals. Could use s because these are called secant lines when they connect two spots. But I have m. I'm going to use the f of 1 again because I know it goes through that point. And then plus m times x minus 1. And so there we see it. I'll zoom in a little bit more. And if I come up here and slide that point where I'm taking h down to 0, notice how the slope of the two lines looks to be becoming the same. I hit 0, and they are the same. And then I go past that, make it negative, and it starts moving out the other way. Okay, so everybody, you agree that it looks like that limit as my h or delta x goes to 0 ought to produce the right slope? Seems reasonable. Looks like it, at least on the graph. And so that's what we want to do. There it is. Okay, so that's what we're going to do with this, is just set up that limit process to create our slope. And then once we have our slope, we can always make our tangent line. And so we have our definition of the derivative at x equals c for some function f of x. Now, so since it's a limit, we know that some limits don't exist. So it could be that we have something that doesn't work or doesn't have that limit. But our definition here, we can call it f prime at c. Okay, that's one definition, or one notation for a derivative is you put a little prime up there. Decimals knew what that was, so that was wonderful. So our definition here is the limit as, and I'll use delta x like the textbook. Delta x goes to 0 of f plus delta x minus f at x over delta x. And again, what's happening on the bottom is I'm taking x plus, oh wait, sorry, messed up. We aren't quite there yet. We need c's in there. Okay, this is the definition of the derivative at c. Derivatives actually are defined at a single point. Now, if you get more general and you get the answer for any general value of x, oh, then you can create this derivative function. But derivatives are defined at a point, typically. And again, what's happening in the bottom is I'm taking c plus delta x minus c. But the c's disappear, and I just get delta x. Okay, this is just the slope between 2 points. That's all that thing is, but we're letting delta x go to 0. So we're shrinking that the distance between those points down. Okay, and there you go. If this limit exists, we have a derivative. If the limit doesn't exist, we don't. And so, an example using our x squared. If we have f of x equal x squared, and we want to use, say, x. Now, here's the funny part, is, I could say x equals 1, or I could say c equals 1. Kind of doesn't matter. But you see, if I follow exactly how this definition is written, I should write x equals 1. But it's also possibly more clear to a person if I say c equals 1. So it's, you can go either way with that. I'm going to say x equals 1 in line with that definition, but if I said c, that would be okay too. So we want to do this at x equals 1. So let's look at f prime of 1. According to this is the limit as delta x goes to 0 of, now, again, here's where you need to be careful. It's x squared. So when I do x plus, c plus delta x, or 1 plus delta x, it all has to be inside the square. Okay? And when I say that to you all, you're going, well, of course. Okay? But when you actually go to do it, many people screw it up. Okay? It's just one of those things we screw up usually at this stage. So I have the 1 plus delta x quantity squared minus 1 squared and over delta x. And now, again, with these problems, the game is always the same. Okay? The game is to try to turn that numerator into delta x times something. Right? Because right now, I'm dividing by 0. And every time I do a derivative this way, I am dividing by 0. yet this limit usually exists for most of our nice functions. And so there must be a way to kind of fix this. And, well, usually you just start multiplying things out and see what cancels, and hopefully life turns out wonderfully. And so we have the limit as delta x goes to 0. So I multiply everything out, and I get 1, 2 delta x, plus delta x squared, minus 1, all over delta x. Now there, I do see those are gone, and now I have achieved what I need. I have the limit as delta x goes to 0, and in the top, each of those terms has a delta x in it. And so I can pull out delta x and a delta x here, and then the rest of the top was 2 plus delta x. And I could have it over 1 if I wanted. But at this point, then, I get to use my limit property and say, oh yeah, here the limit of that thing is 1, so I don't have to worry about it. And now I can just use direct substitution here, and so I get 2 just like decimals did. Then, if I needed to go on further and actually produce the tangent line, right? What's my formula for the tangent line? Well, I can do that too, because now I have the slope. And if I'm finding the derivative at a point, well, I always have a point, right? X is 1, y is 1 squared. Okay, so I always have the point, and then I just have need the slope there. Any questions on that? Okay, now, of course, sometimes it doesn't work. So, for instance, here's an example 2. Suppose my function is 1 over, we'll go with 1 minus x. And I want to look at that at x equals 1. Well, I have a problem, right? F of 1 is undefined. So right there, no good. I'm done. Can't do it. All right, so that won't work. Okay. So, you can have perfectly nice function, 1 over 1 minus x, a perfectly nice function, but if the function's undefined, I'm not going to be able to find its derivative at that point. Doesn't, seems quite reasonable. Now, we can have other funny things, though. So, like, now, you run into this issue with limits, right? Sometimes you can only do a right-hand side or a left-hand side limit, or if you were to try doing both, you get different answers, something like that. Suppose we have f of x is equal to the square root of, let's go with x minus 1. Something like that. And we want to do this at x equals 1. Okay, something along those lines. Well, in this case, f at 1 is defined, but it is not defined to the left of 1. okay, because we'll get a negative number. So that would be a problem. In that case, we'll just try it with a right-hand limit. We'll move in from the right and try it that way. So you can do that at these spots where, you know, functions cease to be defined. We can still take a one-sided derivative. And so here, I'm going to say f prime of 1 is equal to the limit as delta x goes to 0 from the right. So I'm going to add something to 1, but I can't let delta x be negative. You know, in this one, delta x could be negative. In the decimals thing, I used the slider and I made h negative. Right? It can be negative, not a problem. But in this case, we have to limit it to being positive. And so now, okay, I take this and I have x plus delta x minus 1. And then minus x minus 1 under the square root like that, and divided by delta x. Oh, wait, I didn't put 1 in. Sorry. Makes my life a little easier if I do that. 1, 1. So this is really nice because, right, when I put 1 in there, I get 0. That's awesome. So this is equal to the limit as delta x goes to 0 from the right-hand side. Here I just have the square root of delta x and minus 0, so that's great, over delta x. And unfortunately, in this case, not a lot I can do. Okay? Because now, I could simplify this simply by saying that's 1 over the square root of delta x. Another way to look at it is, well, the top has the square root of delta x. The bottom has the square root of delta x squared. So I could factor out square root of delta x over square root of delta x. That's 1. But I'm still left with the problem of, you know, this is the limit as delta x goes to 0 from the right of 1 over the square root of delta x. And it's a good thing we studied infinite limits, because now we, you know, there would be an asymptote here at 0. Okay. Now, and since we're only coming in from the right, it is defined and so forth. And in this case, it grows without bound, you know, up toward infinity. And so here I actually can just write equals infinity. Okay, so it's undefined, but it's undefined in this particular way. It grows without bound in a positive direction. And so here we have the case where the function was defined. It was defined just fine. Okay, but we do this limit process and we find out that what's happening is that the slope of that tangent line, you know, or well, that tangent line there, as we define it, would be straight up and down. Okay, so a function may not have a derivative, even though it's a perfectly nice function. Okay, it may not have a derivative at a particular point. Okie doke. So we're at the end of our time. I will get, you know, as much as I can posted as early as I can. But again, the nice part is you do have homework you can start on that's listed there. You can start on your discussion item. And it's not like everything's so crammed together. We've got 2 weeks to kind of get things done. Okay, any questions, parting questions? All right, well then I'll see you on Thursday.